My name is Brady Forrest. Thank you very much for having me here. VLab has a great reputation, and it's a real honor to be involved in an event here. Quantum computing it gets a lot of hype. There's a lot of hyperbole. We don't know if this will be the next big thing or when it will come. And I think, in a lot of ways, this kind of sums it up. We don't quite know, how to feel about the space, maybe. And unfortunately, we see a lot of quotes like this. But that same type of quote was said about the internet. That same type of quote was said about the mobile phone until the iPhone. That same type of quote is still being said about VR. But there are a lot of people involved in this space right now who are really trying to make this happen. And I feel like there's a lot of evidence on the side of quantum computing moving forward. And part of it has to do with just this next speaker who, just given his stature and the fact that he's able to explain quantum computing, really says how far it's come. Please meet Canadian Prime Minister Justin Trudeau. Maybe.
I was going to ask you to explain quantum computing, but when do you expect Canada's ISIL mission to begin again? And are we not doing anything in the interim while we prepare?
Okay. Very simply, normal computers work by... Don't interrupt me. When you walk out of here, you will know more. Well, no, some of you will know far less about quantum computing, but most of you, normal computers work either there's power going through a wire or not. It's 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. Regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing, and that's what we're doing. Don't get me going on this, or we'll be here all day, trust me.
And hats off to Justin for that one. But just to correct him in one spot, we're not aiming here for a smaller computer. We're aiming for a more powerful computer. Each qubit that gets added increases the power of that computer exponentially. Unlike when you add one transistor, and it just increases it by that one transistor. And so when you hear about a 60-qubit platform, it is exponentially more powerful than an earlier stage one. And so in this panel, we're going to dive into the technology in this space. We're going to look at how this is going to affect security and your Bitcoin wallets. We're going to look at what it's like to be a startup in this space. Where will you find the talent? What does it take to get through VC diligence? And we'll hear from the investment perspective what it's like to invest in this space. It's so nascent, that requires so much money. And then finally, we'll end looking at this from a global perspective. What does it mean for China to be laying out 10-year plans? I just saw Germany today laid out a 10-year plan on AI. I'm sure they're thinking about quantum computing, and yet the US does not seem to be moving forward in the same way that I wish it were. So with my panelists, we'll dive into all of these topics. And throughout the session, please text in questions. I don't know everything that you want to know, and Rajesh will be moderating the questions, and I'll get them, and around 8 o'clock, we'll start diving into them. So we will cover these 5 topics with these 5 contestants. And before we go too much further, just one final quote from a famous physicist. We are dealing with the edge of physics here, and trying to bend it to our will, and we will see where we go. So please welcome up the CEO of Bleximo. They are a venture-backed startup in the quantum computing space, Alexei Marchenkov. There you go, sir.
Thank you very much for inviting us to this event. It's a great honor. So the company is called Bleximo. It's actually Greek for entanglement, right? So this is a key property of quantum systems that allow much more powerful computing than any classical system can. And I'm going to speak about near-term practical quantum computers. This is because this is what my company is building. A few words about the company. I'm a career physicist. I spent over 25 years in quantum physics, solid-state physics, low temperatures, and more than 10 years in what's now called quantum computing. So I even was a professor, tenured professor at Georgia Tech, and for 2 years, between 2014 and 2016, I worked at Rigetti Quantum Computing. That's probably now the largest dedicated quantum computing company in the world. I was the third person in the room, though. And then in 2016, at the end, I left to pursue a bit different approach, and I'll tell you a few words about what we're doing. So we're based at the Lawrence Berkeley Lab. We're part of the Cyclotron Road Incubator. So this gives us access to all the DOE facilities. It comes with funding from the Department of Energy, but we're also venture funded. So the lead investor is ENIAC Ventures. And the pitch to them was very easy. What guys are you guys building? We're building the ENIAC of quantum computers. That was, a very powerful statement. So we also have a few partnerships that allow us to work on relatively small budgets. We do not buy any hardware. We use partnerships and facilities at national labs to demonstrate the first prototype. And Berkeley Lab, the Molecular Foundry in particular, this is the microfabrication facility, and a few commercial companies are our partners. So there are several platforms, several leading quantum computing platforms that are known today as potential candidates for useful quantum computers. Superconducting qubits, superconducting circuits is what we do because we can. And we are particularly focused on building application-specific processors. I'll tell a few words about why later on. So a very simple fact is that quantum computers will always have errors. Qubits are very sensitive to ambient noise. It takes just one photon to destroy a state of a qubit during the calculation. But we cannot do error correction by copying the state of a qubit. Fundamental laws of quantum mechanics prohibit that. So therefore, we're stuck with the error rate of about 0.1% at this moment. So that's quite a lot. Right, so this means that there is almost a certainty that if you have a 100 qubit system, that it will decohere in about 1 second or even less than that. So that's not much time. So the current state of the technology is frequently called NISQ, which is noisy intermediate scale quantum. It refers to processors with about 100 qubits, and that will not use any error correction, have a minimal error correction. And to make practical systems, you need help of digital classical computers. So this is a summary of what can be done near term from our perspective. You cannot do the well-known, exact quote-unquote quantum simulations, or do encryption break-in, exact encryption break-in, or do Grover search. But what you can use quantum processors as coprocessors to classical system, and you can use so-called approximate quantum algorithms. They were developed about 3 years ago, and the most famous one is so-called variation quantum eigensolver. So what it is, essentially you have an optimization loop where you use a classical computer to prepare the state of the quantum processor. Then the quantum processor makes a calculation that's difficult for classical computer, for instance, evaluating the wave function of some complex molecule or material. And then you use that result and the classical optimization loop to converge to a certain value. For instance, if you want to calculate the binding energy of two molecules, right, you need to minimize the binding energy. So that's how most companies that work in the space think about practical quantum computing at this point. And we believe that we'll be doing this for a while. All right, so who cares? Many industries, for instance, if you talk to pharma spends about $75 billion per year on new drug development. And out of 10,000 candidate molecules, only one makes it to an FDA-approved drug, and it takes on average $2.5 billion in about 10 years of time. So if we could eliminate those candidate molecules that are likely to fail during expensive preclinical and clinical trials, We can save, even with minor improvement on the selection process, billions of dollars. So we don't need to revolutionize the industry. We need to do things better, cheaper, or more precise than conventional computers can do. So you can ask, well, but there are millions of atoms in the typical drug-protein interaction. But the fact is that you don't need to simulate the whole system quantum mechanically. You really need to simulate only the interaction region. This is a well-known method called QMMM, which combines quantum and classical calculation. It actually was awarded a Nobel Prize in 2013 in chemistry. So that's our approach. So this is the first line of attack for the company. So it's not just pharma, but this is quantum simulation, right? Simulation of quantum systems, quantum molecules and atoms interacting with each other. This is the simplest thing to do because on one hand, you have a quantum system that you need to simulate. On the other hand, you have a quantum chip, right? So we call it mapping. It's the easiest thing to map one quantum system into another so that your quantum processor simulates the behavior of the quantum system that you are studying. And we call this application QASIC. This is Quantum Application-Specific Integrated Circuit, because we believe that we can have improvements and actually do a faster demonstration if we make the architecture of a quantum processor for a particular task, right? So we do not generate, basic topologies where you have to map your problem on the basic topology. So think about a particular problem, like interaction of molecules, and make chip that run these kind of simulations. So this is how we, I think, differ from the other players in the market. So there are a lot of challenges, technology challenges, right? So first and foremost, it's qubit count and coherence. They cannot be one without each other. Just making 1,000 qubits is not going to do any good if you do not increase the coherence time, right? So qubit connectivity is the other one. So the aforementioned exponential increase in computing power happens only if each qubit on the circuit talks to every other qubit. But in real life, you have adjacent qubits to talk to each other, and that the power of the processor is thus reduced to a low value. So scalability, so the technology has to be scalable. So for our particular case, there is the difficulty of getting signal to qubits that sort of are in the center of the chip from the plane geometry, so we need to come from the third dimension. Costs are high. Typically, you need several tens of thousands of dollars per physical qubit just in cables and electronics and refrigeration system. Control complexity. So the system is very complex. To run algorithms on multiple qubits, you really need very smart algorithms that control the circuits and actually make sure that the calculation you've done is a useful calculation, not just some kind of noise. And finally, and this is what I call better algorithms. This is joint work with theoretical physicists who actually simplify quantum mechanical problems that can be written in a very general form to a much simpler form, so it's easier to map those Hamiltonians. That's the function that we're optimizing on a processor, and thus do the efficient calculation. So I'll leave you with this slide. We can talk about this later, but these are verticals where we think NISQ era will yield some near-term applications. First of all, the problem class is quantum chemistry or complex system modeling, right? So the aforementioned drug design, new materials. In fact, when you optimize a Hamiltonian, you can also think about the classical cost function that you can optimize within the same optimization loop as you do with a quantum system. It's just that you need to create a chip that maps the classical problems well. Then optimization in general, that's what I just talked about. And then it's a buzzword, but machine learning essentially is optimization problem with random sampling, right? So I'll be happy to discuss more about our technology after the panel is done. Thank you.
All right, now I'm just going to introduce our panelists, and then we'll get going right up there. Lewis, if you could just introduce yourself.
I'm sorry.
Sure. So I'm Lewis Parks. I'm with SecureRF. So we're not building quantum computers, but when Alexei's successful, and in a few years from now when there's a large enough one, there are two algorithms, Grover's and Shor's, that are mathematically proven that they will break the asymmetric or public key cryptography that we rely on today. And my partners have developed mathematical models and engines that actually, in a Diffie-Hellman-like public key system, replace the math and are quantum resistant, there are 5 or 6 platforms that can produce quantum resistant security technology. What's unique about us is that we're particularly small. We've done software development on 8-bit 8051 processors to protect things with public key or digital signature algorithms, etc. Why are we sitting here today? Because although a large enough quantum computer, maybe some distance off, I was at a conference on Tuesday, and best guess is 10 years, could be as early as 5. China is not announcing their progress as IBM and Google are, so we don't know. But I guess the key consideration is, if you think about, let's take cars that have a 3-year design cycle, on the road, it built for 7 years and post-production 7 years, average age 11.6, so now we're at 14.6 years. So the semi-autonomous vehicles being designed today with little or no security will be around when nation states will have access to these engines and models. Smart grid, building infrastructure, et cetera, will be around for decades. Aerospace platforms, a lot of things being built today that arguably, if they're not looking or considering quantum resistant technologies, will be at issue and things that we'll be using in our lifetime. So we partner with the semiconductor industry. We're active in the automotive space, embedded medical, building infrastructure, and elsewhere in terms of providing licensing IP and models from my partners. That's what we do. And I should say immediately, the name's a bit of a mismatch because we started 14 years ago looking for the smallest processing platform we could, which was a UHF passive RFID chip running at 1 megahertz. So that was our target computing platform for our methods, hence the name SecureRF. But we're on RISC-V, ARM processors, et cetera, automotive platforms doing secure boot, secure load, et cetera, as a in-production functioning quantum resistant company.
I just checked, SecureQC is available on Twitter.
You talk, I'll be right back.
Somebody else may have already grabbed it. I apologize, I should have whispered it to you.
You're not
and now
helping.
I'd like to introduce Pete Shadbolt.
Yeah, so I'm Pete Shadbolt. I'm a co-founder of psiQuantum, which is a startup company based here in Palo Alto. We're building a general purpose error-corrected quantum computer using silicon photonics. So I got started as a physicist working on rubidium ion single photon sources. So a physics experiment, a perfect qubit or single photon source in an ultra high vacuum environment, kind of the antithesis of what our company is trying to do. And then I moved to Bristol University, where our CEO, Jeremy O'Brien, had started a research group to take lithographically fabricated waveguides, the same waveguides that are used in top-of-rack switches and data centers, to manipulate the states of single photons and build quantum computers where we encode quantum information using light. There I got to work on early instantiations of qubits and gates and algorithms on chip. So a chip that's made in the same fab as the CPU in your phone. I actually worked on the first instantiation of the variational quantum eigensolver, so simulating helium hydride on a 2-qubit chip, which was really, really fun, great times. And then, saw those chips become bigger and bigger. All of that time I was working as an experimentalist. I transitioned to work as a theorist at Imperial College London with Terry Rudolph, who's another of our co-founders, on the fault-tolerant approach. So the error-correcting codes and the architecture that we use to build a general-purpose quantum computer using single photons. And then around 2015, we had some breakthroughs in the hardware, especially in the silicon photonics platform, as well as in the architecture, where we found new good ways of doing fault-tolerant optical quantum computing that led us to start this company. So 2015, moved to Palo Alto and raised some money and got started.
Great.
All right. And now I'd like to introduce Hratch.
Yeah. Good evening, everyone. My name's Hratch Achadjian. I lead the business development team for Google's quantum computing effort. Our focus is primarily around building a general-purpose superconducting gate-modeled quantum computer. I do want to take this opportunity to thank the VLab team for putting this event together and giving us the chance to be up here.
That's it? How'd you get there? How'd you get to Google?
A lot of hard work and a lot of time.
What did you do before Google? What did you do before Google?
So before Google, I was at a small company that was a systems integrator. It was a startup based in Los Angeles called SADA Systems. Grew that company successfully from about 20 employees to about 150 by the time I left. Great experience there, so that gave me the introduction into systems, and then moved over to Google Cloud and now Google Quantum.
Cool. Thank you.
Yeah.
And our newest panelist, so unfortunately, Shruti from Array Ventures was unable to make it tonight. We miss her presence, and luckily for us, Joseph Raffa was able to jump in and kind of take the investor perspective. He's with IBM Ventures. Joseph, if you could say a few words.
Oh, thank you. Yes, I will do my best to fill her shoes. I know it's a tall order. And I'm very excited to be here on the panel. I'm very excited and grateful for being included and for all the work you're doing to put this together. Joined IBM about 3 years ago. We are making quantum computers. I work in the Almaden Research Facility down south of San Jose, up in the mountain there in Santa Teresa, and I'm director of IBM Ventures. We are interested in startups, as you can imagine, that are of potentially strategic import to IBM, and quantum computing is one of those categories. We are very interested in quantum computing and have a long-term strategic interest in quantum computing. Before I joined IBM, I was a financial VC. I was a partner with Adams Capital here in Palo Alto, focusing on deep technology investments, university spinouts, other research kinds of spinouts. And before that, I was the CEO of a startup, fabulous semiconductor company making chips for digital cameras, acquired by MediaTek, founded in Japan. And I really got my passion for deep technology when I was a general manager and VP at Synopsys in the mid-90s down in Mountain View. And I saw firsthand the power of how innovation could really disrupt a big industry. And I continue to be passionate about it, including quantum computing.
Awesome. Well, let's get started. And thank you all for being here tonight. And let's just start simple. How did Justin do? Did Justin explain quantum computing well? What would you add to his explanation?
How much time do we have?
You have all the time in the world.
I think one of the key points that we often try to stress and is important for a group to take away is, you're going to hear a lot and read a lot of headlines around qubits. And it's not just the number of qubits that matter, but similar to what Alexei said, the quality of the qubits, how they interact together, and that you need both halves of that to make a functioning and useful computer.
So if you were going to layer on what quantum computing might be used for in the future, what would you have added to Justin's explanation?
It's a very large question. So in terms of where it can be useful, I think the applications across industries are vast. A lot of them are yet to be discovered, candidly. But the areas of interest in research, Alexei again touched on one of them around organic chemistry and drug discovery, certainly around security and encryption, much further down the timeline and the horizon. But in the near term, organic chemistry, quantum chemistry is a fascinating starting point for us. Also within the financial sector, for example, if you're optimizing, let's say, a portfolio of assets, the ways of doing that today are very computationally intensive. You might have a machine learning model that's applied towards that, but maybe in the near term there's an opportunity for a hybrid classical quantum neural network that might better be able to yield results before we get into a full-blown quantum neural net.
Pete?
Yeah, I think that it's something that it's actually surprising to me that this sometimes gets lost in the discussion around quantum computing and the applications for quantum computers, which is that, if you look at the history and the source of the excitement about what we are doing, I think it's a product of two things. First of all, general purpose computing is an extraordinarily powerful idea. Turing completeness is a miracle. The fact that your CPU can execute arbitrary code and calculate any function is a miracle as far as I'm concerned. And when you couple that together with the fact that we're talking about an exponentially powerful machine, human beings are very bad at reasoning about exponentials in general. And what goes missing is the fact that we're not talking about a machine that's going to speed up things. We're talking about a machine that's going to solve problems that are otherwise impossible, meaning that if we do not build a quantum computer, in 1,000 years, there will be sentient beings on some planet somewhere that have code that they want to run to solve problems that they care about that they will not be able to execute. And so that binary nature between totally impossible and possible sometimes goes missing in a fog of kind of speed-ups and advantage and things like that. So I think that's something that I try to emphasize and kind of promote, yeah.
And where do you see us on the time horizon?
As far as having a machine?
Mm-hmm.
I think we'll have a machine on a timescale that's acceptable to venture capitalists. Let's put it that way.
Wait a minute, I thought, are any of your investors in the room?
Well, the lights are very bright.
And this may end up on YouTube.
Seriously, I mean, that's what I think.
Yeah. Alexei?
To add to what I said, well, it was a pretty good explanation. I just can say that Feynman was right. So I don't understand quantum mechanics, but I know how to use it. So I see things work, and my approach is, just making things by doing them, right? So we do observations, we iterate on designs, and I think that with superconducting quantum computers, or quantum accelerators, as we call them, or NISQ processors, if you like. So we'll see something on the horizon of 3 to 4 years that will show definite improvement in comparison to what just purely classical systems can do. So that's how.
So as we try to develop a machine, what languages and programming disciplines are going to emerge? How is that different from current programming disciplines? No thought to the tool makers? No thought to the next great
No, I think it's a great question. I think part of it comes down to...
Take us one at a time from the end. I'm happy to start.
Yeah, no, dive in.
You first, and then I'll...
All right, I'll finish we're mid-thought, and Joseph, you can chime in, certainly. I think the nature of quantum computing is fundamentally different from classical computing. So the skill set of computer science certainly helps, but the understanding of even physics at a basics level is an additional sort of skill set that the ideal programmer would inherit, right? They need to have the foundations of physics, quantum mechanics, plus computer science, and when you get those three elements in a person, they're going to be best suited to start interacting with tools like Circ, which is our software development kit for quantum computing. Having an understanding of how these machines might work will certainly help in playing around with the software and programming.
So you'll have to abstract it somewhat. Joseph?
Well, I think the starting point to thinking about programming is just looking at the reality of what's happening at the physical level. And the reality of what's happening at the physical level is that in modern quantum computers, the state of the art, we have a relatively small number of qubits that are noisy. And this is the great challenge, is in isolating these atomic particles and then controlling them, entangling them with each other. This is very challenging, and the systems are very fragile. So in order to program one of these, you need to be operating down at that level of what's happening at the physical qubit. You need to be able to understand, see what's happening, and you need to be able to have a way of controlling what's happening. And this, unfortunately, at the moment, the great challenge, of course, for the quantum information scientists is to be able is to figure out how to take a problem or an algorithm and map it into an environment where there's a lot of noise and a lot of small things that can impact the calculation. So the tools themselves today require working at a very low level of abstraction, down at the assembly level or below, down at the level of controlling the pulses that actually impact the atomic particles. This is called pulse control. It's important to do that right now. Beyond that, there are lots of very smart people working at higher levels of abstraction to try to solve some of these applications, like quantum chemistry simulations, financial portfolio simulations where there's a lot of risk in the simulation, artificial intelligence, machine learning, et cetera, et cetera. We'll talk about that later. But the starting point today is really very much down at the physical level with regard to tools. Now we're trying to make it easy. I'll give a plug for IBM. We're trying to make it easier for the world to do this. We've put our quantum computers out on the web for free. You too can go and create an account and start programming and run a real quantum computer right now. We have about 100,000 developers around the world that are running our quantum computers, and they're working at that level. They're down at the assembly language level. They can see on their screen all of the little physical things happening, the noise, the pulses, the timing, and they need that to do their job. So it's pretty low-level stuff right now.
And how long does it take for a programmer to kind of map their head to this new paradigm?
That's a great question. We're finding, now that we've had experience with lots of different kinds of people using our quantum computers, we're finding that it's easier for people to start from scratch. In fact, some of the best quantum programmers are high school students because they are not encumbered by all of the tools and frameworks that exist for classical computers. They can look at a problem with fresh eyes. Those fresh eyes, I think, are the essence of the innovation in quantum computing right now.
So if a startup wants to get hiring, they should just head on down to Palo Alto High?
You'd be surprised what's coming out of that place.
Louis, what are your thoughts as we're talking about programming in quantum environments and the security of our various crypto wallets?
So we're kind of on the other side, so to speak. So quantum computing is really exciting. If anybody's seen a picture of one of these labs, they recognize that this technology will not be in the iPhone 22. It operates at a very, very low temperature. I think it's just a challenge getting code and things down there and back up again. And that's being solved by some very brilliant people. Conventional computing is probably going to coexist for quite a period of time, as we know it. And that's where we're operating. So in fact, although we're looking at those problems and we're monitoring the advancement, being risk averse, generally speaking, as we all are, we're on the other side monitoring the speed at which they're successfully building these units, because at a given size, and Microsoft says 2,300 qubits, some people say 4,000, and again, it's discovery, true discovery that's going on, but at some size there are at least 2 algorithms that will break everything you're using today. So, well, weaken it and one will break it. So we're on the conventional side working with both software and hardware engineers and our semiconductor partners to develop algorithms so that you will be protected at the time where these computers are sufficiently large. Earlier this week, I heard, I would say the consensus was 10 years-ish. Could be significantly longer. I think the biggest
quantum computing resistant crypto and encryption?
Where it's going to become a critical issue.
Mm-hmm. We don't know the solution to the shield, but we know that the sword may be coming around that time.
The train has left the station, but we're still laying track at the other end.
Yeah. At one point, so I think your services might be required faster in 10 years. So the same approach as I discussed, variation quantum eigensolver has recently been applied to an algorithm that's called variational quantum factoring. So there's a paper 2 months ago by a startup called Zapata. They're based in Boston. And that uses the same approach. So you have an approximate algorithm that tries to break basically the factor, a large number and 2 prime numbers. So we're looking into that and see whether that's a viable approach. But on paper, it looks very interesting. And the fact that an approximate algorithm that will require much fewer qubits and maybe using NISQ qubits, like noisy qubits, is capable of doing that is a recent development.
I should just add that what we do and what we're specifically focused on, where we started, was very, very small processing platforms. So there's an interesting intersection which makes it significantly challenging, and that is this thing called the IoT has significantly enhanced the value of small processors, 16 and 8-bit processors, to control critical functions, whether it's an embedded medical device or your car or the infrastructure. So ironically, technology that we have today, like elliptic curve cryptography, will not run nicely on an 8-bit processor or a 16-bit. So again, we mostly drive around in unprotected cars. These are large 100 million line plus code networks with no protection, and layer autonomous on top of that, airplanes, et cetera. And again, so even before we get to quantum and the complications it's going to raise, we're already struggling with securing literally billions of devices that we're wearing, that we're plugging into our homes, putting on our kids and our cars, et cetera. So it raises the landscape significantly in terms of what we're looking to address when you add quantum.
So Joseph, when you hear about all this fear coming down the pipe and the advances Alexei and Pete are making, what do you think with your investor hat on?
Let me answer it from both the IBM perspective and also the venture perspective. The long-term threat is real for security and threats to encryption. The question is, how long will it take for the quantum computers to be sophisticated enough to be able to actually start factoring prime numbers in an efficient way and cracking the current encryption schemes. Depending upon who you ask in the scientific community, you might hear numbers like 2,000, 4,000, 8,000 qubits need to be available. That's significantly more than is available today from the current providers, from the current quantum computing developers. So as a financial VC, I would say it's going to be a while before the threat actually becomes material. However, there are definitely certain kinds of applications that benefit from being protected now. Some things are going to be around in 10 years, right? There's data sets that are going to be around in 10 years that are sensitive. There's infrastructure that's being built right now that's going to be around in 10 years that's going to be vulnerable. Those need to be protected maybe immediately. We have a project in IBM Research where we are developing lattice-based cryptography, which is quantum resistant. We are actively, that's public knowledge, we're actively discussing that with companies and governments as to how to help them with that, and we're actively helping external organizations protect themselves with these algorithms. We've also submitted them to NIST as a standards candidate. So if that, I believe there's some meetings coming up early next year at NIST in order to determine which of these proposals gets accepted. If it gets accepted, then now we have a methodology for protecting data against quantum computing hacking.
And how do you evaluate quantum computing startups with your investor hat on?
In general? Mm-hmm. Oh, well, the starting point is to look at what they're doing in the context of the entire quantum computing infrastructure. There's, I don't know if you have that slide, but there is a slide. Maybe I can just talk to it verbally. I put together a slide that takes apart the quantum computing industry into all its different pieces. And so, for example, a company that's making hardware is very different than a company that's making an app. They're both quantum startups. The investment thesis is different. And also, a financial VC will look at them differently than a strategic VC. In my current role at IBM, I'm a strategic investor. So I'm looking for companies that have a potential strategic relationship with IBM. When I was a financial investor, I'd be looking for a company that could generate a good internal rate of return, IRR. And those are two very different ways of evaluating startups. I can go on into detail about any of that if it's helpful.
I think it'd be interesting to hear how you look at it. If you had a investment perspective, how you would evaluate the talent and what you'd be looking for now, given where we are in the cycle.
Yeah, well, as a financial VC or as a corporate VC?
As a financial VC.
As a financial VC, of course, I'm motivated by one thing, it's IRR.
Yep.
And
that's where the majority of the funding that's going into this cycle is coming from.
Pardon me? I'm sorry.
Is that IBM legal?
Yes, that's IBM legal. They told me I have to stop talking. Sorry about that, guys. So you can just erase that from the YouTube presentation. There's a time component to IRR. And that's very important in this industry because the question is when, and I think you all probably know enough about venture capital to know that VCs buy preferred shares of stock in startups with the hope of selling those shares down the road at a significantly higher price. They buy and then they sell. And they get a return based on the difference in the price. So they're trying to create a valuable, help create a valuable company that can sell for a much higher price. But the IRR aspect of that includes a time to exit. So that's particularly challenging in quantum computing, right? Because it's not clear when the quantum platforms themselves, the hardware, will be at the point where it's sophisticated enough to be disruptive enough to enable, for example, a software app company to be able to really grow in a nonlinear way, which is a prerequisite for getting venture returns. So as a financial investor, looking at the software startups, I would be skeptical because of the sheer amount of time it takes that I think it will take to get to an exit. Now, what I would look for in a company like that, I'd look for a few things. Firstly, I would be looking for the A team in terms of scientists. They have to have the A team. And this is all about innovation, intellectual property creation. They need to be able to invent disruptive technologies. Also, as you know, the A team attracts the A team, the B team attracts the C team. So from the perspective of long-term health of the company and long-term innovation, the A team has the best chances of continuing to attract the A team. That's one thing I would be looking for as a financial investor. But at the same time, I'd be looking for a CEO and some governance around the company where they can find a way to generate some cash flow between now and that inflection point. I think it's going to be a long road ahead for software startups before they get to that inflection point. And so how do they keep themselves alive between now and then? What are the sources of cash? Is it going to be non-recurring engineering? Is it going to be consulting? Is it going to be some other source of cash? If it's just venture capital, I would be concerned because it's a long time. They're going to dilute the company, and then you get too many VCs sitting around the table, and then the board meetings get very complicated, and it gets very hard to operate the company eventually. And the expectations are too high, right? So a lot of unhealthy things happen when you have a long period of time where there's no revenue. VC industry is not really geared up to that.
Yeah, sounds like drug discovery.
What's different about drug discovery? Okay, drug discovery is more similar to the quantum hardware companies because, and I do think there is a financial investment thesis on the hardware side, and it's as follows. If you can find a quantum hardware idea that is disruptive, there's a 10x improvement, maybe it can disrupt the incumbents, for example. You get a group of very smart scientists together and you write a lot of intellectual property, you write a lot of patents. There are still a significant number of large corporations around the world that are making IT platforms. Maybe they're making systems and servers. Maybe they're in the networking business. Maybe they're in the cloud business.
Maybe they're in the room.
Probably, possibly in the room, who knows? They're in the US, they're in China, they're in lots of other places. several of them would like to have quantum computing platform in their offering at some point. And they would be prospective acquirers of quantum hardware startups. So I think there is, like as Vijay Pandey was saying in his presentations at Andreas and Horowitz, it's this sort of build it and flip it type of an investment thesis. You run like crazy for a few years, you build a legitimate platform with world-class scientists, and then you sell it. That's a good way to make money and a good way to make a good IRR because it doesn't take a lot of time. Yeah.
Pete, what was your experience raising?
I let Jeremy do it.
Yeah, but you must have watched from the shadows.
No. So I was a postdoc who had spent my entire life in the UK when we came out here to raise Series A. So I had never had a real job. I'd barely been to the US. And so it was pretty interesting to start taking a bunch of meetings with Silicon Valley VCs and talking about the architecture and the hardware that we'd been working on. And it was very gratifying to see that people are very clued up and ask smart questions and are willing to be optimistic about the future. And it was really good fun. Diligence was very high quality. I was surprised at the quality of people that came out for that.
And how are you attracting talent for your startup?
So
where are you looking? What are you looking for?
Okay, so we're attracting talent, I think, by having a differentiated approach to start with. We are certainly doing things a little differently to the rest of the field, I think. And in particular, we've made a strong emphasis on, I guess, two things. So on fault tolerance, on error correction, where I think we got a lead early on, and that's really helped to attract people who care about error correction and fault tolerance to our company. And we're also, because of our hardware platform, we're able to hire a disproportionate number of conventional semiconductor engineers, systems engineers, designers who have no quantum information background at all. And that's made things easier, I think, in many respects. 3 of our co-founders were formerly full professors of physics in the UK, so that also helps as far as just having a network that we can draw upon. And they've been working on quantum computing for the last 20 years or so that's also helpful.
If someone wanted to get into quantum computing, this is a question from the audience, what would you recommend they do to any of you?
Go to Palo Alto High School.
Yeah.
I want to just comment.
Let's just assume they would get arrested for doing that. So maybe a second option.
That's a good point. I agree with a lot of Joseph's thesis, particularly on the hardware side. But I think a couple of things should be pointed out. Certainly geographical differences. So we're signing production contracts now for quantum resistant methods because they're quantum resistant, but we're relatively new. Old security is better than new security. Anybody who works in the area will tell you. Why? Because it's been unbroken for longer. Everything is either not broken yet or broken. NIST right now is a 7-year process. So at the end of 7 years, they're going to pick some winners. There's 80 people competing. We're part of it. So forgetting everything else, we have a 1 in 80 chance. I mean, there's going to be some consolidation because there's many lattice-based methods. There's many multivariate, many hash, many code. But it's a 7-year process. If you wait as an enterprise for the winner to choose, you're going to have some significant issues. And it's already a little scary. We know of industries who wait, arguably until the litigation rises high enough to make a change to their product. Hopefully it's not a life-threatening thing. But I've already been at least at one meeting where I've had a team tell us they're very interested in pursuing quantum-resistant platforms, and think of these as large, monolithic things that take many, many years to roll over. But senior management doesn't want to pursue it because if they discover there is a solution, whether it's code, hash, multivariate, or us, it means they will then now need to proceed with a multi-billion-dollar investment because they know there is a problem. Kind of like you don't want to test your networks if you know you're going to find something. So there's a lot of dimensions when you're talking about when to invest, when to pursue, et cetera. And it's different from here to the EU. Same company here. Checkbox must be quantum resistant. You go to the same company headquarters in the EU and they go, yeah, we know about it, but that's not the issue of the day. So I think there's a lot of things in either choosing when to invest or when to pursue or what have you. And the hardware and software are very different animals.
Justin?
By the way, just along those lines, also wanted to add that we are productizing quantum-resistant algorithms in the short term. It's public knowledge that in Q2 of next year, we will be including those in our storage solutions. So IBM makes storage technologies for installed big storage systems, and they will include the quantum-resistant algorithms early next year.
Just a reminder, if you have questions, just text that number. Hratch, where is Google pulling their talent from?
Well, VLab events. I got 2 resumes tonight, so
all right.
It's not a bad place to be.
Is it from proud parents? Or?
Proud parents, some younger talent in the room as well. So it just seems to follow the free massages, I guess. But it's, I think it's challenging for everybody out there, realistically, right? It's not just the larger players building the computers or the startups, but even those that would, let's say, be future customers need to really hire this talent in-house. So aside from the race towards hardware, I think there's actually a race for talent. I hear numbers like there's 1,000 qualified quantum resources in the world. And sitting here tonight, thinking of the broader talent pool that we can even hire from, the US puts out, I think, less than 1 million STEM graduates a year. I could be a little off on that number. But we're in a distant third relative to other talent pools. India's putting out close to 3 million. China's putting out close to 5 million.
And our immigration policies are not
helping, yeah.
No.
So I think it's a challenge for everyone. But it's going back to what I said earlier, a combination of that quantum mechanics, physics, computer science hybrid is a good mesh that we're looking for.
Now, when we did our call last week, you wanted to talk about where does the application go? What is your?
Yeah, so I think the application is actually a tricky piece, maybe even cart before the horse. So a lot of what
you said chicken and egg on the call.
Yeah, both fit. It's very likely that as we work towards a useful quantum computer, that there will be a bit of a winter until useful applications actually arise. Mm-hmm. And right now, we're so early in the stage, yet kind of as you put it on our call, max hype cycle. It's difficult, I think, for people like us in the room to actually make sense of what's going on. And from our perspective, before we even get to the applications, a fundamental understanding of, look, there's different types of hardware out there. I was kind of alluding to it earlier, and not all qubits are equal, but you also need qubits and quality. And when you look at it, you've got analog devices and you've got digital devices. Companies like IBM and Google are working on a digital general purpose quantum computer. Companies like D-Wave fall into the analog category. They have different advantages. An analog machine has high qubits, but also lots of noise, is really only focused on optimization type problems, whereas a general purpose type machine is going to have lower qubits, but is going to be more general purpose in use when it comes to market. There are so many different ways you can tackle this question. I think first you just need to understand not all quantum computers are equal. The applications for those machines are going to be different. And it's going to come back to, look, let's get a useful machine out there, and then the applications after some time will follow.
Joseph? No? Another question from the audience.
Yes. I do have something I want to say. We are. I agree with most of your points. At the same time, we are aggressively pursuing several ideas around the strategic value of quantum computing to IBM. And we're being persistent and vigilant in our research around that. So let me give you an example. A couple months ago, we published a paper out of our Yorktown research group investigating the possibility of using a quantum computing platform to simulate a piece of an AI system for supervised learning. It's called a kernel that's used for classifying data. Simply speaking, it's when you train up the expert system, the kernel allows you to determine, when a new data point comes along, is it in this bucket or is it in that bucket? You train it and it goes one way or the other. Now, when the data is complex, the kernel that sifts through that data is also complex. And in the state of the art of artificial intelligence right now in that particular application, it could be a line, it could be a plane, or it could be a hyperplane with many dimensions. And when that hyperplane has a large number of dimensions, calculating it, the cost of calculating it grows exponentially with the number of dimensions. And this is a real problem in AI. It very quickly blows out the capability of classical computers because of the complexity. And we're finding seems like it's a good fit for quantum computers. That was the essence of the paper that was published. So why is that important? That's important to us because IBM is a big company. We're an $80 billion company. Our mission is to provide enterprise solutions through a hybrid cloud environment long term. One way to differentiate those is through artificial intelligence. If we can use quantum computing to create a disruptive artificial intelligence capability in an enterprise solution because of this phenomenon, then it will leverage a lot of IBM business down the road. And therefore, this all makes quantum computing very strategic to IBM. That's why we're spending money on it, and that's why we're sticking with it.
You don't want to be disrupted.
We want to be the disruptor
yes.
in enterprise solutions. Yes, that is our goal. And we think quantum computing is one of the ways to do that, potentially.
Well, Alexei, who do you think is going to get disrupted as quantum computing?
You mean the company, the industry as a whole? So, well, we are all in this competition, so there are different approaches, there are different platforms. I do believe that there's not going to be a single winner or a disruptor, so we'll probably be evolving in terms of complexity of the calculations we can do, speed, cost, until we finally overcome. We need to compare with existing solutions that can be, existing problems that can be calculated by existing supercomputers. And there are different metrics you can compare by cost, by speed, or by complexity of the system. So I'm thinking that it's more like an evolutionary process at this point. And we need to work on the technology much harder, right? So we need to increase coherence, we need to increase the quality of qubits while increasing the qubit count. We need to find smarter ways of controlling the qubits and do error mitigation. So there are ways of not doing error correction, but mitigate errors, noise errors, by using machine learning algorithms and correcting the way you control your qubits. So again, the lowest hanging fruit seems to be quantum chemistry. It's the easiest problem easiest if you can tell about anything in this field as easy to solve, right? So we, as a startup, we operate again on funding stages, of course, right? So we don't have long runways as IBM or Google.
When are you expected to have revenue?
You want me to talk about the model I presented to investors? Well,
whatever you want to share.
Honestly, we're actually generating some revenue, but we're doing a little bit of quantum engineering work. So my team consists, and we're hiring primarily engineers, right? There is a lot to do in microwave engineering and protection of qubits that physicists cannot do. So it involves complex finite element calculations and actually calculating systems that consist of multiple qubits, tens and hundreds of them. And that requires an industrial approach and people who have done this before. Right, so we do some engineering work, generating some revenue. It's not though, the quantum revenue. So you can think about someone buying our solution, our specific solution, maybe 2 to 3 years down the road as a down
2 to 3
payment.
years?
I think we can land some. I mean, D-Wave sells machines, right? So it's a great example, right? So this is something everyone doesn't know that it really provides quantum acceleration. There's no proof. Maybe it's never done that. But they keep selling machines that cost like $10, $15 million, right? So big companies and national labs and I think governments are interested in training quantum force, like workforce for that. That could be, you know, an early revenue source for a company like us.
Hratch, do you have any thoughts on D-Wave's computers?
Several thoughts in general. I think, you know, the quantum annealers we've had experience with have been a great starting point. But the reason we've gone in the directions we have as a company are really around, it's been difficult to prove in a scientifically rigorous manner that our output experienced a quantum advantage or speed up, right? When we go to market, or if we're up here on stage, you know, representing a company like Google, we have a reputation of having some of the best engineers in the world. And so the last thing I want to do is add to the hype of anything, but really focus on delivering a machine that, you know, when we do open up to the public and is accessible via our cloud, is actually going to be quantum hardware, is actually going to yield meaningful, scientifically verifiable results. So, you know, that's always been our philosophy, and kind of backs up with our reputation of our engineers as well.
What industries are you guys selling the D-Wave servers to?
So to clarify, we're not selling D-Wave servers.
Oh.
If I alluded to that in any way, that wasn't my intent.
Mm-hmm.
We will in the coming year hopefully be releasing a cloud service on our own quantum hardware. What I meant to say earlier, what I tried to say was, we did start experimenting around D-Wave hardware several years ago. Mm-hmm. There's one located at NASA Ames Research Center, not too far from here, obviously. We since moved away from that approach. We've built our own gate-modeled superconducting general-purpose quantum computer from the ground up. So our approach will be to open that up via the cloud, to clarify. Does that answer your question? Or?
Mm-hmm.
Okay.
Thank you. A question from the audience, and this is to the floor. Are pharma and biotech industries already interested in quantum computing? And by interested, I think we mean investing.
I would actually back up from that question.
Yeah.
I would say there's interest across the board from almost every industry and every vertical.
They are, but the question is at what stage they can become your customers and partners at this point. So my impression is that big pharma companies expect more finished solution and demonstration of quantum advantage in some way. After all, again, it's about costs of drug development, and it comes either from like cost of running particular calculation or running more precise models. So there is interest. It's just talking. You need to talk to the right people and see whether you can partner early on in developing systems for those particular industries.
The answer is yes. I think any pharmaceutical company with substantial research department, in other words, a large number of scientists that has the potential to be disrupted by quantum computing, they are actively investing some at least amount of scientific labor, some scientist time to learn about quantum computing and to experiment with something. They will allocate some percentage of their scientific capability to do that. They are today doing that, and some are paying money, some are not, but they're definitely spending time. And in that kind of industry, scientists' time is the scarce resource. So yes, I see it across many very large pharmaceutical companies.
Yeah, I totally want to follow up on what Joe said. That's exactly my experience. You asked earlier, who's going to get disrupted? Mm-hmm. You can kind of tell because they're doing something about it. So, pharma, automotive, banks, bioinformatics, all of these guys over the last few years, we've seen the transition from their CTO will come and take a meeting with us and say, oh, quantum computing is interesting. Yeah, we want to hear more. Tell us what you're doing. To them saying, we have a team of between 1 and 10 people internal inside our big incumbent organization that is dedicated to figuring out quantum computing. They've written this code. We'd love to, figure out how we get this thing up and running, and so on and so on. So that's been you can just count by numbers that transition over the last 3 years, I would say.
So back in 2016, the NSA released or leaked a memo talking about the end of encryption. Was that all hype? Was that, how did that affect the industry, and what are your opinions?
I guess, so it's not hype. And it is a pretty interesting life cycle, because you start off in the mid-'70s, well, actually in the '80s when you had a computer big enough, you run RSA, and then Diffie-Hellman came along at the same time, but in the mid-'80s you had this thing called ECC, and it took until the early 2000 when NSA said everybody moved to ECC, and of course ECC, the nature of the algorithm, is actually going to be broken before RSA on a smaller qubit machine. So now the NSA has come back and said, if you haven't moved, don't move. And of course, RSA will not fit on many things that ECC will. The banking industry in particular has an issue for performance purposes. So there's a bit of a conundrum there and a mixed message. As a matter of fact, there's a great paper that Neil Koblitz wrote about why are they doing this to us and the politics behind security. So again, on a large server farm, whether you're using New Hope or any of the other lattice methods at Google, at IBM, life will be good. But the end of your financial system is a chip and a card in your wallet. That's the end of the network. And arguably, you want to be secure down to that point. And there may be some challenges in doing that. So I don't think it's hype. I think it's a real call to arms. Many people are dealing, 80 entities, a lot of them academic, combined with a lot of great corporations have submitted to NIST, and ETSI is busy. We were at ETSI in Europe this week for the post-quantum meetings, next month in China, et cetera. So a lot of people are focused on it, and I think it's real. The issue is when.
All right, a question from the audience. Since quantum computing does not calculate arithmetically, is it a computer or probabilistic statistics?
It's a very good question. So it's, well, as in classical computing, you can actually do any calculation by using 1 and 2 qubit gates, right? So it doesn't use zeros and ones as classical gates. It uses qubits, right, and entanglement to do that. So it's a computer nonetheless in the end. So when you run an algorithm and measure your qubits, actually they will be in zeros and ones, right? So that's what happens by the end of the calculation. And you have to figure out, based on these zeros and ones and you input, what this result means. And this is the difficulty in quantum algorithms, right? Especially with few qubit processors. So there will always be error, and quantum processors are probabilistic. So errors are going to be, the answers will differ from run to run. It's difficult to predict, although there has been a paper recently, what you get on the output of the calculation, whether it's a true calculation you were, influenced by noise and in your system. So that's something that every company that claims that the quantum processor works, or quantum computer works, will have to demonstrate. So you'll have to compare your quantum calculations side by side with a calculation done on classical computers. Until classical computers, you will overcome the limit, right, where classical computers just choke because of the complexity of the calculation. And that, to me, is the test on whether your quantum computer really works. So that's the way we are going to demonstrate our technology, that it's viable, run it side by side with a classical calculation.
And
I don't know
another,
if it answers the question, but.
Just a comment on that, which
yeah.
Quantum computers can efficiently simulate classical computers. So if you have a true quantum computer, anything that you can do on a classical computer, you could in principle do on the quantum computer. You would take the same gate sequence and you would run it on a quantum machine. That would typically be a very bad thing to do because it would be very expensive and wasteful, and you'd be much better off doing it on a classical machine. But just from the point of view of understanding the nature of the machine that you're dealing with, I think it's helpful to understand that quantum computing is a strict superset of the classical computing that we do today.
I think that one of the clarifying points around that question is whether or not the qubits are error corrected. If the qubits are, the state of the art today is that the qubits are largely not error corrected. So that means there's a large amount of noise present in every calculation that's done. And it smears the answer statistically across a wide variety of possibilities. And in order to find the answer, you need to run the calculation thousands of times and look for a pattern, maybe a peak somewhere, measure the peak, and that's your answer. So that is very statistical. After the qubits have been error corrected, which is a big challenge in quantum information science, and a lot of people are working on that, then I think it'll look more like traditional computing.
All right, we just had a bunch of questions come in. So Pete, this one is aimed at you. Psi has said that they may be able to produce a working million-qubit computer in 5 years. This seems way beyond most quantum hardware companies when they talk about it in that time frame. Why are you so far beyond what other quantum hardware companies are trying to do?
Yeah, so we have very aggressive timelines. Obviously, there are error bars on that. We're building hardware. Things get delayed. But I think the basic premise of what we're doing is the following. If you plot a graph of the number of qubits that people have been able to make, real qubits, in any platform, ion traps, superconducting qubits, phosphorus and silicon, whatever it is, you can look at the gradient of that graph and extrapolate out into the future and figure out when we are going to have a million-qubit useful machine. And it's not a very encouraging picture. The rate at which we've been able to increase the number of qubits on the chip is not good. And so basically, when we started the company, we said, you have to do something different. We had spent nearly 10 years in academia making increasingly large systems of qubits and measuring them and publishing lots of papers and taking this academic approach to getting things done. And when we started the company, we were very clear that the magic ingredient that is going to accelerate progress, and it may or may not, we can succeed or fail, is if we can effectively deploy the existing tools of the semiconductor industry. There has been $1 trillion of investment into the tools and the practices and the organizations and the capability that exists, in this valley and elsewhere. And that, as far as I'm concerned, is a near science fiction-like manufacturing capability. So the premise of our company is that from the very beginning, from the very get-go, we will get as fast as possible into a real 300mm manufacturing line. We will never make small systems of qubits. From the very beginning, we are taping out millions of devices on a wafer. Those devices are not good enough. They are way below the error correction threshold. But we're going to iterate in that degree of freedom rather than making incrementally larger and larger devices. And our bet which, you know, we'll see how that plays out over the next few years, is that that's going to allow us to accelerate towards a useful machine in a meaningful way and buck the trend that we currently have today that is not acceptable.
All right, we are nearing the end, and I just got 10 questions. So we are gonna, this is now a lightning round, plus I have like 1 or 2 at the end. So can the panel give me 1 or 2 examples of classically intractable problems that quantum computing can solve now or in the near future?
Anything, any molecule above like 10, 15, 20 atoms, let's say, is intractable. So the amount of memory that's required is, there's an IBM example that like caffeine molecule, it was 23 atoms, requires 10 to 48 bits of memory to simulate. That's about 10% of the atoms of the Earth. On the other hand, if you talk about qubits, it's about 200 qubits that can process the same amount of data.
And the other one is breaking all encryption.
Just to clarify, today there is no machine that can outperform a classical computer. It does not exist today.
Can one of you explain Show's algorithm in intuitive terms? Nope. Okay. Hratch, does Google have a roadmap that you can share?
Yeah, if everyone here wants to sign an NDA.
Okay. Yes, I swear they will.
No, nothing I can share on stage.
Okay. All right, moving on. When will quantum computing be on my iPhone?
Well, just to put this in perspective real quick, right? A quantum computer is a lot of the things we're working on right now is probably the size of this podium. First off, it's shielded from magnetic interference, seismic interference, and then it's cooled to about 300x colder than the ambient temperature of space. So for that, and it's suspended from a rig that's much larger than this, by the way. For that to get to your iPhone, probably not tomorrow or the next version of the iPhone, as you said.
But just to comment on that, you know, every time you use Siri or you know, Google Assistant, you effectively have a, you know, warehouse scale data center on your phone in some sense. So obviously you can talk to these things over the internet. It doesn't have to be co-located. Yeah.
Why don't we see more collaboration between large companies like Google and IBM? When you look at this is from the audience. This isn't me. Don't look at me like that. You know, when we see, you know, there's open source work like TensorFlow as examples where folks are working together.
Well, on the topic
is
of
IBM legal going to call again?
Let me just say we're very open to collaboration in a very broad sense. We are actively collaborating with hardware and software startups in quantum computing. So it's our belief that right now, given the early stage of the industry, that it's important to invest in the infrastructure. And that involves finding a way to work with everybody. We've open sourced our development tools, and we're encouraging the hardware vendors to download them and try them. And we're making our platform available freely to all the application developers and encouraging them to try it. You know, the reality is, in the most aggressive forecasts, right? You can look at all these forecasts for quantum computing out there as an industry, and you know, I don't have an official one, but if I just listen to what people are saying around out there, maybe 5 years from now, it could be $500 million on the top line, maybe $1 billion max on the top line, right? And numbers are all over the map. But let's say it's $1 billion on the top line in 5 years, for example. It's not my number, but let's say, you know, you got to pick a number. We're an $80 billion company. And so our interest in quantum computing is finding ways for it to move the needle on the top line for IBM. That makes it strategic. So the actual revenue of quantum computing is not really the main point. The main point is the strategic leverage of quantum computing technologies in delivering a much bigger solution to our customers, more valuable solution. We can go out and close $100 million, hundreds of millions of dollars deals with quantum computing under the hood.
Okay,
and that makes it very easy for us to think about collaborating with everybody, including other big companies. So we're quite open to it.
All right.
I want to thank all our panelists, Brady, Alexei, Louis, Pete, Hratch, and Joseph. Give them all a big warm